Let's solve this question. It is not actually one question. I given you 5 questions here. So what is that the information is given is, one is virtual address space. Virtual address is given. Virtual address means the number of bits in the virtual address, and then page size is given. Page size means the frame size and page size, and then page table entry. Page table entry is nothing but how many bits are present in each page table entry, and it is given in bytes. 4 bytes means 32 bits. Okay, and now the question is, and assume that it is all byte addressable. Byte addressable means the smallest addressable unit is byte, or word equal to 1 byte, right? And now they are asking, what is page table 1 size, what is page table 2 size, what is page table 3 size, and how are you going to split the virtual address? Okay, so what is that they are asking is, it is a multi-level paging question, right? So it is very simple. I'll solve it. Maybe for one question I'll explain you in detail what is happening, and from next question we should be able to solve it fast. Okay, so first thing is, for the first question, first one is, virtual address is given as 48 bits, right? So this is given in bits. Virtual address is all given in bits. 48 bits, 64 bits, 72 bits, 72 bits, 72 bits. So virtual address space is given as 48 bits, right? And then virtual address space. Therefore, virtual address space is going to be 2 power 48 bytes, because it is byte addressable. Byte addressable means each word is byte. So since it is byte addressable, I am going to write it as 2 power 48 bytes. If it is word addressable, and word is 4 bytes, then I have to write it as 2 power 48 words, and then later convert it into bytes, right? Okay, and then page size is 16 KB. If page size is 16 KB, page size is 16 KB. What is 16 KB? 16 KB is 2 power 14, right? Then now how many pages will be present? Number of pages will be equal to virtual address space divided by page size. So what is virtual address space? 2 power 48 divided by page size is 2 power 14. Then what do we get? Number of pages equal to 2 power 34. This is the number of pages, right? So once we get the number of pages, right, then we have to find out the page table size of the first level. See, this is what I am talking about, the first level page, I mean PT1, right? Okay, or which way should we this should we number this? So in this question my intention is page table 1 is here, which means if this is the process, right, and if it is broken into pages, then I am calling this one as page table 1, and then I am calling this one as page table 2, and then I am calling this one as page table 3, or you can come in the other way also, right? So no problem, but then you should be clear about which way are you using. So in case I am using this one as page table 1, then I am going to go ahead with this. Okay, so the number of pages in the page table 1 is 2 power 34. Therefore page table 1 contains 2 power 34 entries, and size of each entry is 4 bytes, therefore 2 power 2. So which is nothing but totally it is going to be 2 power 36 bytes. That is the size of the page table 1. If that is the size of the page table 1, 2 power 36 bytes, will it fit in this, which is 2 power 14? It will not fit. Therefore again page table 1 has to be divided into many pages, right? So now again I am going to divide this 2 power 36. See, the page table size is 2 power 36. Now I am going to divide into pages, right? So divided by page size is this much. Then how many pages I get? I am going to get, I think, 22. So 2 power 22 pages I'll get, right? So in the next level page table, I'll get 2 power 22 pages, and size of each page table, 2 power 22 entries, because in this level if there are these many pages, in the next level there will be those many entries, isn't it? And into these many, which is nothing but 2 power 24 bytes. Therefore the next level page table contains, size of the next level page table is 2 power 24, right? And now I'll again divide this into many pages, because it is not going to fit in one page, right? So now if I divide this, 2 power 24 divided by 2 power 14, then I am going to get 2 power 10. What does it mean? This page table PT2 contains 2 power 10 pages. If this one contains 2 power 10 pages, then how many entries will be there in the next level? 2 power 10, right? Therefore 2 power 10 entries will be there, and size of each entry is 2 power 2, which is 4. Therefore it is going to be 2 power 12. Got it? 2 power 12 bytes. Finally, this one is going to fit in one page. Why? The page size is 2 power 14, and here I got the page table size is 2 power 12. It is going to fit in one page. So if you didn't understand what I did here, watch it. What happened is, initially I had process, and the process size is 2 power 48, and then I divide into pages, and then I got the page table 1, which is for containing entry for every entry is pointing one page in here. Therefore this is called page table 1. That is what I am calling it as page table 1, and it contains the number of entries will be equal to number of pages here, right? And here I got a number of pages as 2 power 34. Therefore 2 power 34 entries will be there, and each entry is of size 2 power 2. Therefore the total size of this one came to be 2 power 36. And again I divided into pages, and the number of pages I got here is 2 power 22. Therefore since I have 2 power 22 pages here, in the next level the number of entries will be 2 power 22 entries, and each entry is going to be 4 bytes. Therefore this is size of the page table 2, right? And then the next level is page table 3. Since this one doesn't fit in one page, I am going to divide into number of pages, and number of pages I got is 2 power 10. Therefore in the next level the number of entries I have is 2 power 10, and the size of each entry is 2 power 2. Therefore the total size of this is 2 power 12 bytes, and this is going to fit in 16 KB. Got it? Now how are you going to split the address? It is interesting. I told you that virtual address is going to be broken up into parts in such a way that each part is going to act as an index in one of the page table, right? CPU is anyway going to contain what is the base address of in one of the registers. It contains what is the base address of the outermost page table. What is the outermost page table here? PT3, right? So it contains the base address of outermost page table, right? And now we have to go into this and find out one of the entries. How many entries are here? If you look at the outermost page table, the number of entries present in this is 2 power 10, right? So number of entries present in this one is, there is only one page, and that page is completely not full, isn't it? Even though the page size is 16 KB, I am using only I think 4 KB, isn't it? So it is not full. So the number of entries in the outermost page table is 2 power 10. So in order to address all the entries, or in order to address each one of them, I have to use 10 bits, right? Therefore from the address, virtual address, the first 10 bits are going to act as the index into the outermost page table. Now base address combined with this index is going to give me one page table entry, which is going to point to the one of the pages of the next page table, right? But then the next level page table, in the next level page table, all the pages are completely full. All the pages are completely full. In this page table, all the pages are not full. That is why I have taken 2 power 10. Got it? This is the total number of entries. But in the next level, all the pages are completely full, and if the page table entry size is 4 bytes, it is very important, try to understand it. If the page table entry size is 4 bytes, then how many entries can we accommodate in one page table, in one page? See, now the page size is 16 KB, right? And page table entry size is 4 bytes, right? And now each page contains many entries, and each entry size is 4 KB. Then how many entries will be present in one page? Number of entries present in one page is 16 KB divided by 4, which is nothing but 4K entries, right? So what is 4K entries? 2 power 12 entries are present in each page. Understanding this? Therefore, this one entry of outermost page table is going to lead us to the one page of the next page table, and in that one page we have 2 power 12 entries, and we have to point to one of the entry. Therefore, how many bits are required? 12 bits. So next 12 bits are going to act as index into the next level page table. Got it? And now that particular entry, whichever you get from this using these 12 bits, is going to point to the next level page table, and next level page table also is divided into pages, and every page is full, right? And this one is going to index into one of the frame or one of the page beginning. But then in order to get into the entry, we have to see how many entries are possible here. Here also each entry size is 4 bytes and the page size is 16 KB. Then how many entries will be present in one page of this page table? Same thing. So how many? 2 power 12 entries. So in order to get one of them, how many bits are required? 12 bits are required. Got it? So 10 plus 12 plus 12. So if you add it, how much is this? 24 and then 10, 34. So 48 minus 34. So 48 minus 34 is how much? 14. Right? So finally we got 14 bits remaining. So this is nothing but the page offset. Right? Why page offset is 14? Because page size is 16 KB. Got it? Therefore, the 10 bits are going to act as index into the outermost page table, 12 bits are going to act as index into the next page table, and the next 12 bits are going to act as index into the next page table, and the last one is going to act as the page offset. So your address is split up like this. So 10 bits as index into the PT1 index, PT1 index, and then the next 12 bits is going to be the PT2 index, and the next 12 bits is going to be the PT3 index, and the next how many? 14 bits is going to be the page offset. Got it? Okay. So now I think once you understood this method, now I am going to directly do, I'm not going to do all this procedure again. I'll directly use the shortcut, which means I'll directly try to do fast, and with practice you too will be able to do it fast. If you are not able to do it fast, you please practice it. Okay. So now watch it. Next one is 64 bits is used for the virtual address, isn't it? And the page size is 1 MB. So virtual address is 64 bits, right? And page size is 1 MB. So since page size is 1 MB, I am going to write it in powers of 2. I am going to write it in powers of 2. So 1 MB is nothing but 2 power 20 bytes, right? Fine. Therefore, the page offset is going to be 20. So how many pages will be there in the first level page table? You can take this 20. Okay, see, so page offset is going to be 20 bits, right? And number of pages or page number for the first level page, the page number required will be, you can subtract this one from this one. See, so 64 minus 20 is going to give you number of bits which are used to represent a page number, which is nothing but 44. So 44 bits are required to represent the page number. Therefore, how many pages will be there in the first level page table? How many pages will be there in the process? 2 power 44. Therefore, how many entries will be there in the first level page table? 2 power 44 entries will be there in the first level page table. And what is the size of each entry? 4 bytes. Therefore, into 2 power 2 bytes is the page table 1 size. So which is combinedly 2 power 46 is the page table 1 size. If 2 power 46 is the page table 1 size, and if I again do it into pages, right, which means if I divide it into many pages of size 2 power 20 bytes, then how many pages I get? The number of pages I get is 2 power 26. 2 power 26 pages I get. If I get 2 power 26 pages in this page table, then how many entries will be there in the next level page table? 2 power 26 entries will be there. And what is the size of each entry? 4 bytes. Therefore, it is 2 power 26 into 2 bytes. Are you following it? Always page table entry size will be same. Either it is first level or second level or third level, page table entry size will be same. Only thing that will be different is the number of pages that is going to vary. right? And now the total size of this is 2 power 28. Got it? And now if I again divide into pages, if each page size is 2, if each page size is 2 power 20, then how many pages do I get? 2 power 8 pages I get. Therefore, the number of entries in the next level page table is 2 power 8 and size of each entry is 2 power 2, right? Therefore, this is the size of the final level page table. Got it? And now how to divide the address? The address will be divided in such a way that we have to index one of the entries in the outermost page table first. How many pages are there in the outermost page table? See, this is very important. Outermost page table contains only one page. Either it will be completely filled or it will be partially filled. In this case, even though the page size is 1 MB, right? 1 MB is 2 power 20. The amount of space that is filled is 2 power 10, 1 KB, which means we are not completely using the page. We have only filled it partially. But then how long are you going to do this paging? Until the last level page table can fit in one page. See, in the previous example also, where did I stop the paging? I have stopped the paging when the last level page table is 2 power 12, which is less than the page size, right? So what is the page size here? 2 power 14. So since 2 power 14 is greater than 2 power 12, I can put this entire page table in one frame, right? That is where I stopped. So when are you going to stop the paging in multi-level paging? Whenever we reach a level in which we can put the entire page table in one page, that is where we are going to stop it, right? And here if you watch it, this is 2 power 28, but it is 2 power 20. I cannot put it in one page. That is why I am going for one more level. So how can you decide one more level is required or not? If the page table is not sufficient or the page table is larger than the page size, you go for one more level. Got it? Fine. And now in the last level, it so happens that sometimes we don't need the entire page. In that case, you have to find out how many entries are present in the last level page table. The number of entries present in the last level page table are 2 power 8. Therefore, in order to identify one of the entry, I need 8 bits. Got it? See, in the previous one, that is what I said. By using these conventions, we might get confused. In the previous one, the last level, this one is called PT3, right? It is called PT1, PT2, and it is called page table 1. Okay. Now, these 8 bits are used to index the last level page table or the outermost level, right? Outermost level page table, which contains 2 power 8 entries. That is why 8 bits are used. Then what about the inner next level? You might get confused and you might think that we had to write 26 here because 26 is here. That is wrong. The total number of entries in this page table 2 is 2 power 26, but we are going to go into only one page of this page table 2. We are not going to look into all the entries at the same time. At any time, we will examine only one page. Why? If I take one entry from here, this one entry will point me to one frame, and that one frame will contain only a part of this page table, and only that part of this page table will contain some page table entries, and I have to choose one of them. For that, I have to identify how many entries will be present in one page of this page table. Now watch this. The page table entry size is 4 KB and page size is 1 MB. If the page size is 1 MB, 2 power 20 bytes, and the page table entry size is 4 bytes, which means 2 power 2 bytes, then how many entries will be present? The number of entries per page. The number of entries per page will be 2 power 18. If these many entries are present per page, then how many bits are required to identify each entry? 18 bits. That is why here 18 bits are required. 18 bits are required to address one of the pages here, one of the entries in this page. Got it? And now the next level means I am going to this one, page table 1. Again here also the same thing. Page size is 1 MB and page table entry size is 4 bytes. Therefore, how many bits are required? Again the same logic. So here also each page of this page table will contain 2 power 18 entries, and how many bits are required to address one of them? 18 bits. That is how I got 18 bits. Now add them all. One is 18 and other is 18 and other is 8. So 18 plus 18 is 36, and 36 plus 8 is 44, right? And 44, and this is 44 is filled up. The total address is 64, therefore remaining bits are 20. So 20 is going to be page offset. Anyway, it is right because page offset has to be 20 bits because page size is 1 MB, right? So page offset size is 20 bits, and then this one is going to be page table 3 index, this one is going to be page table 2 index, and this one is going to be page table 1 index. This is how we can split the address, right? So given any address, we first take the first 8 bits and index into the outermost table, and then take this one and index into the next table like this. That is how it is going to happen, right? And now watch the next one. Now after watching these two examples, you should be able to do the remaining ones very fast. So I'll try to do it. You too please do it like this. See, 72 bits are given, and then page size is the page size is 1 GB. 1 GB is 2 power 30. Therefore, how many pages will be present? So 72 minus 30, which is 42. 2 power 42 pages will be present. If 2 power 42 pages are present, how many entries will be present in the page table? 2 power 42 entries, right? 2 power 42 entries will be present. And what about size of each one? 2 power 2, right? Therefore, this is the size of the first level page table. So which is nothing but 2 power 46, right? And sorry, 2 power 44. Now 2 power 44 minus 30. So 44 minus 30 is how much? 14, right? Therefore, in the next level, 2 power 14 entries will be there, and size of each entry is 2 power 2, which means 2 power 16. And 2 power 16 is less than 2 power 20. Therefore, you need not go for one more level. So only 2 levels are enough, isn't it? With practice, you should be able to do it fast like this. Okay. And now, how are you going to split the address? You are going to split the address this way. See. Now using the first we have to go into the outermost page table, right? So here the outermost page table is this one, and which has completely not filled any page, or the number of entries in the outermost page table is 2 power 14. Therefore 14 bits are required to address this, to find out one of the page table entry. And if I take that page table entry, I'll go to the next one, and in the next level, how many entries will be present in one page? How can you do it? So in the next level, again the same thing. Page table size is 1 GB. 1 GB is 2 power 30, right? So 2 power 30 divided by 2 power 2 bytes. So this is the page size, and this is the page table entry size. If I divide this one with this one, I am going to get number of entries in each page. Therefore, number of entries in each page is going to be 2 power 28. If these many entries are going to be in each page, then how many bits are required to identify one of the entry? 28 bits. So 28 bits is going to be enough. Then we add these two. 28 plus 14 is going to be 42. So out of 72, 42 bits are already pulled out for the page table. Then how many bits are remaining? 30 bits, right? Therefore, this 30 bits is going to be page offset. Logical, isn't it? Why? It is byte addressable, and size of the page is 1 GB. Therefore, having 30 bits as the page offset is logical, right? And what about this one? 14 is going to be the page table 2 index. And what about 28? 28 is going to be page table 1 index. So we need only 2 levels here. Understood this? Fine. Now let's look at the next one. You should be able to do it fast like this with practice. Don't worry, if you are not able to do it fast right away, with more examples it will be easy for you. So next one is, so it is 72 bits, and now if you watch it, page size is 256 MB. How much is 256 MB? 28, 2 power 28, isn't it? Therefore, it is 78, and how many pages I get? So 72 minus 28. So depending on this number, we can find out the number of pages and number of entries in the next level page table, right? So how much is this number? It is 6, it is 4, it is 4, 44. Therefore, number of pages in this page table, in this for this process will be 2 power 44. Therefore number of entries in the page table will be 2 power 44 into 2 power 2, which is 2 power 46, right? And again you have to subtract from 46 28. Then how much do you get? It is 3 here and it is 8 here, it is 1 here. Therefore the number of pages is 2 power 18, right? And therefore the entries in the number of pages in this level, in this page table, is 2 power 18, the number of pages, and the next level the number of entries will be 2 power 18, that will be equal to the number of pages in this level, right? So into 2 power 2 is the page table size, which is nothing but 2 power 20, and 2 power 20 is less than 2 power 28. Therefore one more level is not required. Then how are you going to split the address? Address is going to be split up like this, right? So one way to split up the address is, here it is 18. How many entries are there in the outermost page table? 2 power 18. Therefore how many bits are required? 18 bits are required to address one of them, right? And once you get into a page, right, of the next level, how many entries are present in this? That depends on, again, what is the page size and what is the entry size. Here the page size is given as 2 power 28 and the entry size is given as 2 power 2. Therefore 2 power 26 entries are present in each level, in each page. So if 2 power 26 entries are present in each page, then in order to identify one of them, how many bits are required? 26 bits are required. Now what is it? Add 18 plus 26. How much do you get? 14, and it is 44. And then you subtract from 70 to 44. Then how much will you get? You are supposed to get 28, right? Therefore 28 bits are remaining. This one is going to be page offset and this one is going to be index into outer level page table. See, outer level page table, here I named it as PT2, and sometimes they might name it in the reverse order, which means they might come PT1, PT2, PT3 like this. Anyway, you should be able to find out the difference. And this one is going to be the index into page table 1. Got it? Okay, now the last one. So with this experience you should be able to do it really fast now. Watch it. The number of bits here is 72 and the page size is 16 MB. 16 MB is nothing but 14, right? I mean 24. Yes. So 16 MB is 2 power 24. So you have to subtract 2 power 24. Then what do you get? Here I get 6 and here I get 8 and here I get 44. Yeah. So 48, 2 power 48 pages are present. Therefore how many entries will be present in page table 1? 2 power 48 entries will be present, and the size is 2 power 48 into 2 power 2, which is 2 power 50. And now here that 50, from this 50 bits I have to again subtract 24. I think you are following the logic, or if you don't follow the logic, you just follow the first example. And now it is going to be 26 bits, right? Therefore the number of entries in the next level is going to be 2 power 26, because the number of pages in this level is going to be 2 power 26, isn't it? And the page table size is 2 power 26 into 2 power 2, which is 2 power 28, right? So again in the next level, 2 power 28 minus 24, which is 4 bits. Therefore in the next level the number of entries are going to be 2 power 4 and the size of each entry is going to be 2 power 2. Therefore the total size is going to be 2 power 6, right? Now how are you going to split the address? The address is going to be split up this way. In the outermost page table, how many entries are there? See, the outermost page table contains only, the size of it is 2 power 6, but the size of the page is very much higher. It means that the last level page table is not able to fill up even one page. Therefore you cannot count the number of entries that will be present in one page, because it is not even completely filling one page, right? Then how many bits are there? I mean how many entries are there in one page? 2 power 4 entries. Therefore how many bits are required to index into this? 4 bits. But then in the next level all the pages are completely full. Therefore what you should do is find out how many entries will be present per page. So the page size is 16 MB. 16 MB is nothing but 2 power 28 and the page entry size is 4 bytes, which means 2 power 2. Therefore how many entries will be present per page? The number of entries present per page is 2 power 26, isn't it? Therefore, how many bits are required? 26 bits are required. And similarly, in the next level page table also, you can do the same thing. Here also, the same things apply. Why? Because either the page size or the page table entry size, that will not vary. Therefore, only for the outermost page table you have to compute it in another way, and for all the inner page tables the numbers will be same, right? So this number will also be 26. And now just add them. 26 plus 26 plus 4, it is 16 and it is 56, right? And now 72 minus 56, right? So how much is this? 6. I got 16. I think I'm supposed to get 24, right? Somewhere something has gone wrong. Okay, it is not 26. I feel this number is not 26. I did something wrong here. Okay, watch it once. So one good thing is there is a cross checking here. So the last one page offset should be equal to the page size. I mean, if the page size is 16 MB, the last one should be 24. If I don't get it, then I'll do it again. So watch it. So the page size is 2 power 26, 24, is it? Okay, again my subconscious mind is working here. So 2 power 24, and the page entry size is 4 bytes, which means 2 power 2. Therefore, number of entries in each page is going to be 2 power 22. And in order to identify that each entry, we need 22 bits. Therefore, here it is 22, and same thing is in the next level 2, right? So if I add everything, 22 plus 22 plus 4, then how much do I get? I get 8 here and I get 4, therefore 48. And now I have to subtract it from 72. 72 minus 48, then how much do I get? 4 and then 24. So finally I got 24. That is what I am supposed to get, right? 24. Then I got 3 level paging here, and this one is going to be page offset, and this one is going to be which entry? Okay, let's come from the other side. So this one is going to be page table 3 index, PT3 index, and this one is going to be PT2 index, and this one is going to be PT1 index. Got it? So that is how you could solve this. I think these examples have made some points clear. I think if any question is given on this, you will be able to do it fast. Okay, fine.